Imagine a world where computers don't just crunch numbers like our everyday devices, they bend the very rules of reality itself. That's the promise of quantum computing, and now, for the first time, scientists have a foolproof way to confirm it's not just smoke and mirrors. But here's where it gets controversial. Could this breakthrough finally silence the skeptics who claim quantum tech is overhyped? Or is it just another step toward a technology that challenges everything we thought we knew about physics? In a groundbreaking study released on April 22, 2025, in the journal Physical Review X, researchers unveiled an experimental technique that's like a lie detector for quantum computers. It checks whether these futuristic machines are genuinely harnessing the bizarre principles of quantum mechanics, or if they're merely pulling off an elaborate illusion using tricks from classical physics. This isn't just academic fluff, it's a crucial validation that could reshape how we build and trust these powerful tools. The team achieved this feat by designing a programmable quantum processor featuring 73 qubits arranged in a honeycomb pattern. Think of qubits as the quantum version of the bits in your smartphone, but way more versatile. They trained this processor using a clever hybrid approach known as a variational quantum circuit, VQC, where a traditional computer works hand-in-hand with the quantum one in a loop of machine learning. This iterative process helps the quantum machine refine its performance, much like how a coach guides an athlete to perfect their technique. The real test? Programming the system to hit an ultra-low energy state that's simply unattainable through classical means. By reaching and verifying this state, the researchers provided solid evidence of true quantum activity. It's like proving a car can fly by actually getting it airborne, instead of just simulating the flight on a video game. To grasp why this matters, let's dive into the basics of computing. Traditional computers, from your phone to massive supercomputers, rely on bits that flip between 1 and 0 to handle tasks one step at a time. They're incredible for many things, but they're bound by the limits of classical physics, meaning there's a ceiling on what they can compute efficiently over a reasonable period. Quantum computers, however, flip the script with qubits. These aren't stuck in a single state. Thanks to superposition, a qubit can be both 1 and 0 at the same time, or any blend in between, until you measure it. And when multiple qubits link up through quantum entanglement, a phenomenon where particles stay connected no matter the distance, they can process vast amounts of data in parallel. Picture it like flipping a coin in Tokyo, instantly revealing the outcome of one tossed in New York. That's the spooky action at a distance Albert Einstein famously scoffed at. As you add more entangled qubits, the possibilities explode exponentially, leading to what experts call quantum advantage or supremacy. This is where quantum systems tackle problems that would take classical computers an eternity to solve. We've seen hints of this in experiments like the double-slit experiment, which shows particles acting like waves, but proving it's real in a complex, multi-qubit setup is the real challenge, and it gets tougher with every qubit you add. Enter the Bell test, a method inspired by physicist John Stuart Bell to verify entanglement. It measures pairs of entangled particles in random ways and checks the stats. If the results break Bell's inequality, the boundary of what classical theories predict, then non-local effects are at play, confirming that quantum weirdness is genuine, not some statistical fluke or clever simulation. And this is the part most people miss. Classical computers can mimic quantum behavior to some extent using brute force calculations, like trying every possible combination in a puzzle. It's why we can't always tell if a quantum machine is truly quantum or just faking it. No alarm bells go off when quantum rules are invoked. Scientists have to dig deeper to expose the underlying mechanics. In this study, the researchers tackled that by configuring their 73-qubit processor to reach its absolute lowest energy level and then measuring it. In classical physics, the ground state is zero energy, like a ball at the bottom of a hill, perfectly still. But quantum mechanics allows for negative energies through entanglement. Imagine two balls linked so that one can dip below zero while the other adjusts accordingly. It's impossible without quantum rules. Achieving this negative state, confirmed to be 48 standard deviations below the classical minimum, certifies the system as truly quantum. They even verified non-local connections in clusters of up to 24 qubits, the largest group ever authenticated this way. This technique could pave the way for certifying quantum operations in various designs, spotting when quantum states lose their magic, decoherence, and turn classical, and ultimately fueling bigger, more potent quantum computers. But let's stir the pot a bit. Einstein, the genius behind relativity, argued that entanglement violated local realism, the idea that things only affect their immediate neighbors and have definite properties before measurement. He called it spooky, implying it might just be incomplete understanding rather than a break from physics. If quantum computing proves entanglement is real, does that mean Einstein was wrong, or could there be hidden variables we haven't discovered yet? It's a debate that echoes through physics history, pitting quantum believers against those clinging to classical certainty. What do you think? Is this quantum leap a triumph of science, or are we overhyping tech that might never deliver on its wild promises? Do you side with Einstein's skepticism, or are you ready to embrace the spooky side of reality? Share your thoughts in the comments. We'd love to hear your take.